Okay, so this video is going to accompany the projectile motion video you just watched, and I want to give you a few problem-solving tips and work through an example so you can see what we're doing here. So we're talking motion in two dimensions, otherwise known as projectile motion. And I have a situation here with a projectile. In this case, we're going to imagine it's a car driving off the edge of a 5-meter high cliff, and the car is going pretty slowly, only 5 meters per second, and we want to know how far from the base of the cliff does the car land. So to approach a problem like this, I like to use the strategies where we list our kinematic variables in both dimensions. So let's start here in the x dimension. Well, I know that the car is moving horizontally with an initial velocity of 5 meters per second. For these projectile motion problems, if we neglect air resistance, we realize that there's no acceleration in the x dimension. That 5 meters per second is going to remain constant, which means the final velocity is also going to be 5 meters per second squared in the horizontal dimension. A lot of these problems involve finding the range of the projectile, or how far it goes. And so that's going to be what we're trying to find in this problem ultimately. And the hang time for the projectile, that information comes from the information in the y dimension. How long we're going to be in the air is dictated by gravity. So we have to turn to our y dimension information. In this case, the car had no initial velocity in the y dimension. Its initial velocity was 0. Now that won't always be the case. Sometimes I might want to shoot a projectile up at an angle. And if that's the case, we will have a component of that initial velocity in the y dimension. But in this example, the initial velocity in the y dimension is 0. Our acceleration, we're always going to know, is negative 9.8 meters per second squared. Our hang time is generally what we're going to find from this y data, and our cliff height is 5 meters. Our final velocity is unknown, and I don't believe we care about it for this problem, but we could find that out. So one of the most important equations we use for this information is that the range of a projectile is simply the horizontal component of the initial velocity vector multiplied by the total hang time that the projectile is in the air. And so that hang time, like I set up earlier, that comes from information in the y dimension, basically due to gravity. And so we begin by taking a look at one of our kinematic equations. This should look familiar. Our displacement in the y dimension is our initial velocity in the y dimension times the hang time. Our initial velocity in the y dimension is 0, so that term will be erased. And so we have 1/2 at squared, a being negative 9.8, t being the information we want to find, and our delta y value is the height of the cliff. And I write a negative here to indicate that that's moving down. Our displacement is in the negative y dimension. So multiplying 1/2 times negative 9.8, we have negative 4.9 t squared. Dividing both sides by negative 4.9, we have 1.02 equal to t squared. And square rooting both sides, we have our total hang time is 1.01 seconds. Now we go back to the final key here, which is the range of a projectile is our initial velocity in the x dimension, which was 5 meters per second, horizontal initial velocity, times our hang time, 1.01 seconds, and seconds will cancel, and we end up with our units of meters. 5.05 would be the range, and that is how you do that. Hopefully that helps, and have a wonderful